Hey there guys, in our, now last video for this topic on thermodynamics, we are talking about something called bond enthalpy, which I want to tell you right now is also called bond energy. And what we're looking at is another way to calculate delta H, okay? So we can do so with calorimetry, we can do so with phase changes, we can do so with standard enthalpies of formation, we can also do so using something called bond enthalpy or bond energy. And what it comes down to is what happens during a reaction. And hopefully we agree that what happens during a reaction is an endothermic process and an exothermic process, and one of these is larger than the other, which dictates whether delta H overall is going to be positive and endothermic or negative and exothermic. But the bonds being broken, those reactant bonds that are broken, that is always going to require energy. That's an endothermic process. Whereas the bonds that are formed by the products are always going to release energy, right? Atoms want to achieve a lower state of stability, so they will bond with each other, and that releases energy and is exothermic. So what we can do is use this table of values down here that has a bunch of average bond energies, bond enthalpies, okay, for certain bonds, and we can use these bond enthalpies in order to calculate delta H reaction, very similarly to what we did with standard enthalpies of formation. But what these numbers are is that this, for example, 432 kilojoules per mole, is the enthalpy change required to break a bond of 1 mole of HH, of an H2 bond. And you can see here that this is for a bunch of different bonds that might be in molecules. Now, I want to stress something very quickly, and it's something that we've talked about previously. Previously, we mentioned that multiple bonds are stronger. Well, now we have numerical data to back that up. Look at the CC single bond. That, to break 1 mole of CC single bonds is 347 kilojoules. To break a CC double bond, it's 614 kilojoules. For a triple bond, it's 839 kilojoules for 1 mole of the substance to break apart that bond. So you can see here that this supports what we learned earlier, which tells us that the multiple bonds are stronger bonds, and now we have numerical data to actually back that up. Okay, so I want to talk about what this average term means and why that's the case before moving on to actual calculation. So this chart is just bigger, same one from the previous page, but why? Why is it called an average bond energy? Well, the thing is that these bonds don't often exist in isolation. For example, CH, right here, there is no molecule that is stable with 1 carbon and 1 hydrogen bonded together. That should support what we know previously, right? We know that carbon wants an octet, for example, so there is not going to be no CH molecule just like that. But we do know about CH4. So what we can do is we can figure out the enthalpy change for CH4, okay, for breaking apart all of the carbon and hydrogen bonds in a CH4 molecule. And when we do, we get that the delta H for this process, I believe it's around 1,660 or so. And that means that there are 4 carbon and hydrogen bonds here. These are the 4 bonds that we're breaking apart, okay? This is the amount of energy that it takes. And that means for every individual bond, that takes around 415 kilojoules. Now, you'll notice that this number here is slightly different to this number here. Again, it's an average because this CH bond doesn't only exist in CH4. It exists in tons of molecules, and the different atoms that are in a molecule that they're bonded with definitely have an impact on the amount of energy it takes to break the bond. Okay, but I just want to stress that that's why it's called an average, is because some of these bonds don't exist naturally, okay? There is, for example, no OF single bond, okay? So instead we need to use something such as OF2 and use data from that to figure out, okay, what would it be in terms of the energy required to break 1 bond for OF, and use that data to support it. Okay, so that's why it's called an average, and it's just an important note to go forward. But how can we use this to estimate enthalpy of reaction? Well, we're finally here. So to estimate the enthalpy of reaction, this is the only time that we are going to do reactants minus products. What we're going to do is we're going to use the enthalpy of reaction. We'll use this equation right here. And what this equation says is that the enthalpy of reaction is equal to the sum of the bond energies or bond enthalpies of the bonds broken minus the sum of the bond energies or enthalpies of the bonds formed. So for example, okay, if we use the table of bond energies from the previous slide, okay, and we use this equation, I want to know what the delta H is, okay? And again, only time that it's reactants minus products, okay? So what we're going to do is use the table and figure out what bonds are being broken in the reactants and what bonds are being broken in the products. This means we need to draw some Lewis dot structures. So if I draw my Lewis structures and I take the equation, apologies, I was missing a 2 up here earlier, I just fixed it. But if I take my Lewis dot structures and I write the equation basically in the form of Lewis dot structures, it looks like this. This is really helpful for us because it's going to help me to see that I'm breaking 1, 2, 3, 4, 5, 6 times 2, 12 carbon-hydrogen bonds, okay? And so we're going to take the value from the previous question or the previous slide with the table on it, and we're going to use that value for CH in order to help calculate this, okay? So again, we're using, just like standard piece of formation, we're using tabulated values here to help us out, okay? And this table is also on Schoology. So when I set up my calculation, it should look something like this. Now, this looks a little intimidating, okay? But again, all I'm doing is I've identified the bonds that I'm breaking in the reactants, and that's what's going in this first set of brackets here. And so to break this down just for a moment, because there are 2 moles of this molecule, that does mean 12 moles of the CH bond. There are also then 2 moles of the CC bond, okay? And I've labeled this here to help keep track of it. This is all my bonds in C2H6 I'm breaking. I'm then breaking 7 OO double bonds, which is 495 kilojoules per mole. And then over here with the products, the whole reason why we can use these values when these are the values for breaking the bond, right, is that forming is just the opposite process. And we're saying it's the opposite based on this negative sign right here, which is why it's so important that we make sure we have good brackets. So looking at this, we're going to form 8 CO double bonds, okay, and the negative will get used, okay, we're just using the bond enthalpy number as it is, and then we're going to form 12 OH bonds here, okay, 12 moles worth, that is. And so now I can take all of this and plug this into my calculator and figure out my delta H. So when I type all of this into my calculator, I get that for this combustion reaction, an estimate of delta H is negative 2,449 kilojoules of energy will be released for these exact amounts in the balanced chemical equation. Okay, so this right here, this is bond enthalpy, and this is what we can be expected to do with these different calculations, is to estimate this. So Lewis dot structure is going to play a role in helping it out. There's also going to be a little bit of a conceptual reality that occasionally what will happen is you will break CH bonds, for example, over here, but you'll also form CH bonds over here, and those will kind of cancel each other out. And we'll take a couple of looks at that when I see you next. This is bond enthalpy. Please let me know if you have any questions. Thanks.